Conditional probability is the probability that one event will occur if another event occurs. We usually write conditional probabilities using this kind of symbol. You say probability of A if B or A given B. And this is the probability that A will happen if B happens. To illustrate, we'll look at this example. Suppose we asked American adults if they're happy or not, and rich or not, and classified their responses in a table like this. Okay, each of these is a proportion that represents a particular combination of categories here. If you look at these proportions here, we've got 0.12 plus 0.08, that makes 0.2, 0.28 plus 0.52 makes 0.8, 0.2 plus 0.8 makes 1. So these four proportions add up to 1. Now this proportion right here represents the proportion of people who are both happy and rich. So we could write that, if you think of this as a proportion or as a probability, it could look like this. This is the proportion of people who are happy and rich. This right here is the proportion of people who are rich but not happy. So they're not happy and they are rich. Okay, this proportion right here represents people who are happy but not rich. So this would be probability or proportion of people who are happy and not rich, written in symbols like that. And then this would be the proportion of people who are neither happy nor rich. Now, if you want to figure out the total number of, or the total proportion of people who are rich, you just add across the row there and get the row total. And that's going to be 0.2. 0, and that's going to be the proportion or probability that somebody is rich. Down here, if we calculate this column total, we get the proportion of people who are happy, and that's 0.12 plus 0.28 or 0.4. So 40% of the people are happy, and 20% of the people are rich. Now, if you want to calculate a conditional probability, say the probability that someone is happy given they are rich, you can do it directly from this table. What you do is, if it's given that they are rich, all we need to do is concern ourselves with this row right here of rich people. We don't have to worry about the people that are not rich because the condition is that they are rich, okay? They are rich. So we're just going to look at this row, and we want to figure out what proportion of all the rich people are also happy. And the way we find that is we take the 0.12 and divide it by the 0.2. That's all there is to it. So in terms of working out the math, we just take the probability that somebody's happy given that they are rich is 0.12 over 0.20. But that's the probability that somebody's happy and rich from right up there divided by the probability that somebody's rich. And that works out to be, when you do that division, 0.60. So 60% of the people are happy if they're rich. Only 40% of the people are happy overall. That means that somebody's more likely to be happy if they're rich than if we don't know if they're rich or not. Okay, so that means that since the probability that they're happy if they're rich is not equal to the probability that they're happy, R, being rich, has some effect on the probability of H being happy. That means that R and H are not independent. Okay, we can do a similar calculation for people that are happy. If we want to find the probability that someone is rich given that they are happy, we could look at this column right here. If they're happy, we could ignore the rest of the table over there and just look at this column right here. We've got 40% of the people are happy, 12% of the people are happy and rich. If we take that 12% and divide it by that 40%, we get the proportion who are rich given that they are happy. That's 0.12 over 0.40, and that, again, that's the probability that somebody's happy and rich, this probability, but in this case divided by the probability that they are happy, which is this column total down here, and that works out to be 0.30 or 30%. Okay, now 20% of the population is rich, but among the happy people, 30% of the happy people are rich. So there's a difference there between the probability of being rich if you're happy and the probability of being rich in general, and that means that being happy and being rich are not independent events. So you can use conditional probability to check for independence. If the conditional probability is equal to the unconditional probability, then you could say that the events are independent. And if the conditional probability is different from the unconditional probability, then the events are not independent. In general, this is how we write conditional probability. Conditional probability of A given B is the probability of both A and B divided by the probability of B. Now you notice here the condition is B. That comes after the if. That is also the probability we're looking at down here. So we've got B here, got B down in the bottom of that fraction right there. And that's the way it works. When B happens, we can basically ignore everything else in the sample space outside of B. And the probability of A given B is going to be the fraction of B that overlaps with A. And that fraction is just this. Probability of A and B divided by the probability of B. Now the nice thing about this definition of conditional probability is you can rearrange it and get another probability rule, which is our general multiplication rule for any two events. For any two events A and B, the probability of A and B equals the probability of A given B times the probability of B. Equivalently, it's the probability of B given A times the probability of A. But if you look at this part of the rule right here, if A and B are independent, this expression would be equal to the probability of A, and this would just collapse down to the simple multiplication rule for independent events, okay, the one we looked at previously. Now, to see how all this stuff is sifting into your head, I'm going to give you an example that I want you to complete yourself, and then we'll take a look at the results of this in a few minutes. So what I want you to do is to fill in the blanks in this table. Remember, we've got totals running down the side, we've got totals running across the bottom, and you can figure out the 5 missing values that belong in that table by using basic subtraction and addition. And once you find all that stuff, you can find these things also, and then determine if A and B are independent or not. So you can pause your video, and we'll come back in a minute and look at the answers. Okay, here are the answers. We had these numbers. To find this, you just subtract 0.4 from 1.00. To find this, you subtract 0.55 from 1.00. To find this, subtract 0.22 from 0.4. To find this, subtract 0.22 from 0.55. And then to find this, you can subtract 0.33 from 0.6 or 0.27 from 0.45. And, or sorry, 0.45 minus 0.18. So you can find the missing things, because the totals in the rows and the totals in the columns have to add up properly. Now, the probability of A given B is just the probability of A and B divided by the probability of B. It's 0.22 right there, divided by 0.40 right there, and then that's 0.55, which is equal to the probability of A. So 55% of all the outcomes in the sample space are favorable to A. And then that is also true if we just limit ourselves to this event B. 55% of this 40% is in this category A. And that means A and B are independent. It doesn't matter if B occurs or not. The probability of A would be the same in either case. The probability of B given A is probability of A and B divided by the probability of A. Remember, the condition goes underneath. And that's 0.22 divided by 0.55, which is 0.4. And it's the same as the probability of B. And that also shows that A and B are independent.